Hello, my name is Perdita Stevens. I'm from the University of Edinburgh, and it is an honour and a pleasure to give this keynote for SFDI. The title I've chosen for my talk and for the accompanying paper is Theory and Practice of Networks of Models, and that's perhaps rather an overgrand title. I'm of course not going to tell you everything about the theory and everything about the practice of this topic. I'm trying rather to suggest that although most of what I'll talk about is rather theoretical and even mathematical in nature, because that's the kind of way I work and what I'm interested in, I think sometimes there are elements of the pragmatics of how these things should be applied, and especially of how we should get to there from here, which perhaps deserve a bit more attention than they sometimes get. Hopefully that will become clear as I talk. So in my introductory part, I'm going to talk about why we should be interested in networks of models, what I even mean by models, and what the problems are that we should be interested in. So ever since I came into this subject via having spent a few years as a practical software developer following my PhD in pure maths, I've been interested in what I classify as the fundamental problem of software engineering, which is to say that it's just too hard. I thought this already when I was trying to do it, and I haven't changed my mind over some decades of trying to help students to learn to do it. The way we develop software today pushes the limits of human cognitive capacity in a way which we're perhaps so used to that we hardly even notice it anymore. But I think it's a serious problem, and it's seriously limiting our ability to provide as much software of as high quality as we would know how to make use of as a society. So it would be good if we could do something about this and make software engineering not quite so expletive deleted hard. We have of course made many strides in this direction. The software crisis of the 1960s to 1990s is, thank goodness, no longer with us. And why? I think fundamentally because we've got so much better at getting chunks of processing done within the limited capacity of an individual human brain. We have to some extent come to terms with the fact that there is too much information in any medium to large software development. So you can look at this as being the common factor between several different kinds of advances in software development. We know how to use abstractions on every level. We have much better high-level languages now. We have better understandings of how to modularize software with well-defined interfaces between the modules. We have verification techniques involving abstraction. We understand how to test at different levels of our software. We have explicit models to represent different concerns that we've separated. And even when we think about advances in development processes and we start thinking about iterative software development with bounded small releases, we can see that as being another example of the same thing. We're trying to say, how can we focus attention on a limited amount of information in order that one human being can understand everything they have to understand about a given chunk in order to do the right things and make the right decisions about that chunk before moving on to the next concern. Just a moment, let me say, what do I mean by a model, since I'm already talking about models? I don't mean, lines and boxes. Everything's a model. I'll have more to say about that later. But in particular for this talk, any data source that you might have in mind is a model. And thinking about data brings us even more reasons for being interested in holding chunks of things separately. It might be that you have data governance conditions which force you to hold one data source separately from another, perhaps in a different legal jurisdiction. You might have network limitations which prevent you from bringing everything together. I'm very interested in the fact that we may not be in greenfield sites, so you may very well have legacy data sources which you're not willing to throw away and re-engineer from scratch. You may also have legacy transformations which relate them, and just as I'm using the word model in a very general sense, I'm also using the word transformation in a very general sense. When I say transformation, think about any kind of mechanism for checking or restoring consistency between data sources. Examples of the pragmatic concerns that I think sometimes deserve more attention than they get is that over time and there may be a great deal of time in the lifetime of a very large software system, the appropriate notions of consistency between data sources may change a lot. And so may the amount of automation that we want for the checking and restoration of such consistency. And so it's important that we don't tie ourselves into a situation that doesn't allow us to change those things as our needs change. So the software crisis is dead. We no longer have that fundamental inability to build large software systems that dogged us from the 1960s to the 1990s. But not everything is rosy, because we now have a software capacity crisis. And it's quite easy to dig up figures along these lines, that there are hundreds of thousands of unfilled ICT positions in the European Union alone, that one recent estimate was that there would be 1.6 million ICT professional jobs to fill in the EU by 2030. And sometimes, although interestingly not always, if you survey software companies to find out what their main concerns are, they will say things about being able to hire enough people to be able to have the capacity to carry out all the work that they can adopt. However, at the same time, the unemployment rate for computer science graduates is above that of other STEM subjects. So how can this be that we both have lots of unfilled jobs and we have unemployed computer science graduates? I think fundamentally this is just a symptom of the fact that software development is too hard, because what is happening is that there is a demand, but only for the very best people. Okay, there's a demand for superhumans. And what we should be interested in doing is trying to say, how can we achieve the same or better results more easily? So how can we make it possible for ordinary mortals to contribute in a reliable, dependable way to the development of software systems? And that's what I'm interested in today. There ain't no such thing as a free lunch, is fundamentally what's going on here. Tan Starful. So we've made great advances by splitting the overwhelming amount of data and the work related to that data into chunks, but what we've not made so much progress on so far is supporting the integration of these chunks. As far back as Brooks' Mythical Man Month, it was understood that adding people to a late software project might even make it later. Why? Because individual people holding in their mind different collections of the information about a software system nevertheless had to be able to communicate about their different chunks of knowledge in order to be able to get the whole system built, and that is a very difficult, time-consuming, error-prone process. Integration of software modules, whether it's done as a continuous integration process or whether it's done as an integration phase towards the end of development, is again difficult, time-consuming, error-prone. Going back to the agile development methods as another example of abstraction, we can separate development into small sprints with bounded scope, and that's a great thing to do, but if we're not careful, if we don't integrate those chunks, we can end up building up technical debt that never gets paid off, and that's a problem. And of course, if we have explicit models managing our separated concerns, then we also have the corresponding problems of managing projects that involve multiple domain-specific languages, which then have to be enabled to work together in an appropriate sense. So what I'm claiming, I think, is that today we have quite good techniques that support individuals in temporarily focusing on just one concern, but that's not enough, because our techniques do not yet let people off ultimately having to understand other concerns from the one that they're focusing on right now in order to be able to integrate the concerns again, because that integration is happening largely manually with not very much automated support. And that's why software development is still such a hard job. It's not enough even in the context of software development, it's certainly not enough in the context of data interoperability. Throughout this talk, I'm going to be talking mostly in terms of what happens in the development of large software systems, because that's mostly what I'm used to thinking about, but from time to time I will try to point at ways in which I think the things I'm saying are also relevant in a data interoperability environment, which, as I understand it, is what most of you are likely to be more interested in. So in practice, we can have a model-driven engineering setup, but the models that we're using are not independent. So in this picture, which I have a small bet with myself about how often I can use it in talks going forwards in different contexts, we see a group of people in blue who are perhaps handling some kind of user interaction model. We've got some people in red who are handling some kind of internal data model, and we've got some people down at the bottom left who are using Greek symbols and therefore are perhaps doing something more mathematical. Maybe they're doing verification or safety engineering or the like. And if we've done a good job of separating the information involved in the system into chunks, then most of the time each of these people can work with their own model. They can have a representation of the information that's necessary to their work, and they can record the decisions that they, as experts in that domain, make within their own model. But at some point these models have to be put together in order to generate the actual running software. Currently that's largely a manual process. We would like it, ideally, to be an automatable process, and that's the focus of a lot of what I'm interested in and a lot of what I'm going to talk about. So, in conclusion to the introduction to part one, separation of concerns is a success story within software development, and perhaps more broadly as well. Integration of concerns is not yet a success story. Part two of my talk is about bidirectional transformations, which are abbreviated BOOCs, just because bidirectional transformation is a bit of a mouthful. It turns out that, far from being a niche specialist technology, bidirectionality turns out to be everywhere after you start looking at things that way. I often feel as though I'm looking at things wearing Book's glasses and therefore seeing bidirectionality everywhere. This is not surprising, of course, when you take the view that what we mean by a bidirectional transformation is a means of maintaining consistency between things, between models or between data sources, because I've just explained that that's a fundamental problem that arises everywhere. So it's no longer surprising then that books arise everywhere once you start looking at things in those terms. So a bidirectional transformation is the means of maintaining consistency between models. I'm going to unpack this in a moment. And the essence of bidirectionality is that we have multiple models, multiple separated concerns in the way that we've been talking about, which are simultaneously live and yet not orthogonal. We'll unpack this in a moment. What's a model? I said a moment ago, everything's a model. So my favourite one-sentence definition, going back a couple of decades now, is that a model is an abstract, usually graphical, representation of some aspect of a system. I'm very happy that I only put usually graphical in there, because that now means we can just disregard that if we prefer to be talking about textual models, which we very often are these days. And of course, your model might be a database instance or whatever it might be. So everything's a model. Here are a few examples of things that might be models, and the point is that a model supports the work of a particular group of people, and ideally the model records all and only the information that the group of people who are going to work with it need in order to do their work. And so, of course, having multiple models is a consequence of separation of concerns, and another way of putting it is that a model is a representation of a concern. What we mean by saying that a model is live is that it may need to be updated at some time in the future, as opposed to the kind of situation that you might have in an ideal or idealistic refinement-based development, in which you might imagine that you would first develop a model and then derive a new model from it and throw the new one over the wall and never need to touch the original again. Okay, we know that that doesn't really happen very often in real life. Okay, I'm going to come back to the idea repeatedly of using a bunch of JUnit tests as one model, and the Java code that the tests are going to test as another related model. And in that setting, The ideal refinement-based approach might be that we would first of all write the JUnit tests and then freeze them and then write the code without having ever to modify the JUnit tests again. That's unrealistic, and that's why we're in a situation where we have bidirectionality going on. Now, of course, there would be no problem having however many live models we wanted if the information that they recorded was all completely independent. The whole problem that we have with integrating concerns is that there are dependencies between these different models, and those dependencies have to be managed. Looking at our JUnit Java example, there are some changes which can indeed be made in one model having no impact whatever on the other model, and those are the easy ones. So certain kinds of refactoring of the Java code, for example, might have no impact whatever on the JUnit tests very properly. In other cases, there may be a change that is made necessary on the other side. So if, for example, I decide to change the name of a public method in my Java code to something more descriptive, and that method is invoked from the JUnit tests, then I have to update the name in the invocations as well. There might be many different ways to restore consistency, or infinitely many ways even, to restore consistency, and some of them will be better than others. So I could perhaps come along and say, oh, well, I will simply delete every JUnit test that invoked the method whose name I've just changed, and that's probably not what we want to do, because it throws away a lot of important information in the JUnit tests. And so part of the challenge here is to say we don't just want any old way of restoring consistency between our models, we want a good way of restoring consistency between the models that genuinely is going to save us effort. Bidirectional thinking has fundamentally two different tasks. One is to check whether, I'm going to say, whether all is well, whether the models are properly related, whether they are consistent in an appropriate sense. And the other task is to say, if they're not consistent right now, the other task of the bidirectional transformation is to fix it. So that's consistency checking and consistency restoration. We have a whole bunch of choices. We would like to have a choice about how much to articulate about all is well, and I'll talk through that in a moment. There isn't just one way to express what it is for two models to be properly related. We also would like to choose how much of the consistency restoration task should be automated as opposed to, for example, done by the humans concerned. There are choices of what classes of fixes to consider. Should we be allowed only to change one model, or should we be allowed to change both in order to restore consistency? And what kind of information should we maintain in order to do all of this? Should we just use the models themselves, or should we also expect to make use of trace information or histories, deltas, edits, extra information to help us do a better job of checking and restoring consistency? I'm mostly going to talk in a rather simple setting, but all of these things are included under the general heading of books. So a books is a bidirectional transformation, and what it is a books is an artifact for automating those two tasks of bidirectional thinking, and it might perhaps not automate them completely, it might do a partial job of that. I'm going to talk a bit more about what we would like as characteristics of our bidirectional transformations, but the spoiler and the message that I want to get across is that we do not have, and we are not likely to have anytime soon, one true way to write books. Let's talk about the choice of how much consistency to articulate in our bidirectional transformation. And the thing I want to hammer home is that there is a genuine choice here, and that it isn't just a technical choice, it also depends on the organisational and human factors of the circumstance in which our bidirectional transformation should be used. So in terms of our JUnit Java example, what should it mean for our test suite and our Java source code body to be consistent for all is well? We might say that all is well provided they compile together without error, and that would already catch the problem we mentioned of having changed a method name on one side and not the other. but we might want to get more stringent. We might want to say we're going to say something about there being enough tests, so we're going to say the JUnit file includes a test for every public method. We might even want to say we would like all the tests to pass, although heaven help us trying to restore consistency automatically in that case. We might even imagine that we would also like to ensure that a certain coverage criterion was met. A more stringent notion of consistency is more informative, of course. It tells us more if we are able to check that several artifacts are consistent, and potentially, if the consistency checking or restoration is automated, there is the potential to save more work for the user. So those are good things. Against it, it will of course be more difficult to restore consistency against a more stringent notion of consistency, and slightly more subtly, it will give the developers less flexibility. So sometimes tolerating inconsistency is an important thing to do, for example, while some exploration is being made of what appropriate design choices are, and having a stringent notion of consistency which is required to be restored at various times may remove that flexibility in an undesirable way. Even once we've chosen what the notion of consistency we're going to use is, we have choices about how much consistency restoration to automate, and these things span a wide range, again, any of which may be the right thing to do in any particular organisational setting. So sometimes the right thing to do may be not to automate consistency restoration at all, but instead to leave the fixing to be done by humans, just automating the consistency checking perhaps. In the books community, we often make the simplifying assumption that consistency restoration is fully automatic. It always returns a situation in which consistency has been restored. In practice, transformation engines tend to have the possibility of going wrong, and so it may be that, in fact, if the engine returns successfully, then consistency has been restored, but there's the possibility that it fails and consistency is not restored. And it's also interesting to think about situations in which a bidirectional transformation may go some of the way to restoring consistency. Perhaps it implements the easy parts of consistency restoration, where it's obvious what should be done, but it leaves some work for the humans to carry out. And that's some old work of mine, and there's been other work by others done more recently. I won't say any more about that. So we're seeing that there are different levels of books thinking. We're already thinking in terms of bidirectional transformations if we're thinking about consistency explicitly, and I think that's already a useful thing to do. But the next step then is to check or restore it programmatically, and we might do that using a general purpose language, or we might do it using a special purpose bidirectional language. And in practice, I think we're likely to need flexibility. We're likely to need relationships between different artifacts in a development or different data sources in a federation of data sources, some to be connected automatically, some to have their consistency completely left for the humans to restore, some to be restored in a specialist books language, and this is only likely to get worse, and therefore we really need to have the flexibility to make different bidirectional transformations and different ways of thinking bidirectionally work together in a productive way. Why are we even talking about having specialist books languages? You can, of course, write a bidirectional transformation in a general purpose language. Here's how you might do it. You might have one program to check consistency. All of these programs are going to take one model from each model set. Our consistency checker will return a Boolean, which will be true if and only if the models are considered consistent in their current states right now. And then for each direction we'll have a separate program that restores consistency by calculating a new version of one of the models, leaving the other model unchanged. However, these tasks, which we could of course write as separate programs in Java or our favourite programming language, are tightly coupled, for example, because they all will need knowledge about the structure of the data sources that are being related. And so there are some advantages in integrating their automation in a books program, which is one artifact which specifies both how to check consistency and how to restore it. And that opens up the possibility of guaranteeing sensible joint behaviour, perhaps by having a books language in which you can only write bidirectional transformations which have certain predictable, dependable joint behaviour. So what would a great books language be like? Unfortunately, I'm not going to tell you. I'm going to tell you we don't know. partly because I think the right choice of books language is going to be different in different settings. It's not just that we haven't discovered it yet. So my focus for now is on languages which are consistency first, which is to say I expect the programmer of the book's transformation to be thinking principally about what it means for the artifacts to be consistent, and only secondarily about how consistency should be restored if it is lost. And partly because, sufficient unto the day are the troubles thereof, I tend to think about information poor bidirectional transformations, where the only inputs are the current states of the models themselves. I don't tend to assume that we also have information about how we got to these states, so edit information, nor about how the parts of the models are related at a fine-grained level. Let's think a bit about what properties we would like a book's language to enforce. And going back to the beginning, one of the earliest books languages was Harmony, developed by Nate Foster and Benjamin Pierce. And they started, of course, from the view update problem in databases. And so they were working in this asymmetric setting, where they have a concrete source and an abstract view. And we can abstract from a given source a given view, and that's what we mean by saying that the source and the view are consistent. Okay, we mean to say this is the view which gets abstracted from that source when you apply this abstraction process. Now, the asymmetry of this means that one kind of consistency restoration is very easy. If we change the source to S prime, then there's only one thing we can do. We just have to reapply the abstraction function, and that the result of doing that will be our new view. Now, of course, there might be efficiency considerations, but there's no choice about what the answer should be. Going the other way is more interesting, because we cannot simply compute the whole of a new source from a changed view, because some of the information from the source isn't in the view. Okay? So if we would like to have a sensible answer to that, we would really also like to have some more information available, so that we don't just lose all of that information that was in the old source. And so in this formalism we have a put process which takes not only an updated view, v primed, but also the old source, s, from which to compute a new source, s primed. And this lets us also get the other desirable property, which is to say, if we, it turns out, haven't in fact changed the view at all, then we would also like to end up not having changed the source. In other words, if our consistency restoration process is given models which are already consistent, then it should make no change at all. We call such a thing Hippocratic. I like to work in a symmetric setting rather than such an asymmetric setting where there's a source that contains all the information, partly because I'm trying to model model-driven development situations in which each model is worked with by certain humans, and so its reason to exist is typically because it incorporates some information which is not held anywhere else. You can, of course, kind of simulate the situation using asymmetric bidirectional transformations, but that involves you in inventing some more models that are not already required by the development process, and that has its own disadvantages. Okay. And also, a symmetric setting makes it easier to talk about how stringent a consistency notion we want to use, because it makes this consistency relation explicit. So here's the notation that I'm going to use. I'm going to talk about having a consistency relation R and two consistency restoration functions, one to produce a model from each of the two model sets that we're going to start with. And I'm going to call the consistency restoration function correct if it really does restore consistency with respect to the given relation, and Hippocratic if it does nothing provided that the arguments are already consistent. Okay? And these three things between them form a books. It's worth remarking that I've already incorporated the assumption that one model is authoritative at each consistency restoration, so only one of the models is allowed to change, and it must change in such a way as to bring it into consistency with the model which is not allowed to change. And what we're saying here is, if you like, that in cases of conflict between the two models, we know which one is going to win. Okay, the consistency relevant information from the authoritative model is going to overwrite corresponding information in the other model. Sometimes you might quite correctly say, isn't it better to have a synchronization approach where both models change? That tends to be a bit more complicated, and technically there's a danger of kind of collapsing both models into an uninformative consistent state. So you might accidentally restore consistency by deleting all the information from both models, and then you have to take care to rule out such bad things happening. Keeping one model unchanged is a relatively easy way to keep us honest in this, which is one reason for doing it that way. Correctness and Hippocraticness are only part of what we want from a good books. To look at undoability, let's consider this sequence of model edits and consistency restorations. So we've got M and N when we come in, somebody edits N to N primed, and we restore consistency, thereby modifying M to M primed. And now somebody comes along and puts N prime back to where it started, to N again, and we restore consistency again. Where do we expect to be? If you expect that we're going to be exactly back where we started with question mark equals M, then what you're saying is you expect some kind of undoability. The key thing I didn't specify was I assuming that M and N were consistent when we came in? If we were assuming that, then the property we're talking about here that we wish from our books is weak undoability. If we want this property even if M and N were not consistent when we came in, then we're talking about a property which has variably been called strong undoability or history ignorance. Unfortunately, we can't have either property. Here's a quick example in the Java JUnit case. Suppose we're working with this kind of consistency relation, where we're going to say for every class on the Java side there is at least one test class on the JUnit side whose name is going to have this format. It's going to be test and then the class name and then some integer. And conversely, if we look at any JUnit test class whose name has that special format, then there's going to be a corresponding class on the Java side. The way our scenario appears is, suppose we have a newbie who comes along and deletes one of the classes on the Java side and restores consistency. Suppose that the result of that is that we delete the corresponding JUnit test classes. Then our newbie restores the account class and restores consistency again. Unfortunately, we don't get back to exactly where we started because at this point the JUnit test class is going to be created anew just from the information that's available to the consistency restoration process, which means that it's not going to have any actual tests in it. Okay, it's going to have no content. So this situation was not undoable. Fundamentally, the problem that arose in that example was that there was some information that was relevant to consistency, in our case the names of the Java classes and the names of the corresponding JUnit test classes, which was in some sense stuck to other information that was not itself relevant to consistency. And that was why when we deleted some consistency relevant information, we also deleted some consistency irrelevant information, namely the internals of our JUnit tests. And then when we did the consistency restoration, we were unable to restore all of the information, so we didn't get back to exactly where we started. Now, that's a very woolly and informal idea, so now let's think about how we can formalize it. Information relevant to consistency is maybe better thought of as information that is visible from the perspective of the other model. So here's one thing we can do. We can define a pair of equivalence relations on each of our model sets, each using one of the consistency restoration functions. So the tilde f equivalence that I've got at the top is defined by saying m will be considered to be equivalent to m prime if, whenever we restore consistency with an arbitrary element of n in order to generate a new element of n, the result is the same regardless of whether we pick m or m prime. Okay, so here what we're saying is that as far as consistency is concerned, m and m prime are interchangeable. So after we move over to the n side, no differences between m and m prime remain visible. Okay? Dually, we can do the same kind of trick using the backward consistency restorer, saying, suppose we take some element on the other side, and now we modify one or other of m and m prime to restore consistency with that. Okay, now, if we get the same result regardless of which of m and m prime we start with, then what we're saying is, no matter which element n we choose with which to overwrite the consistency relevant information, they come out to be the same. In other words, the only differences between m and m primed were the ones that were relevant to consistency. So all of the differences between m and m prime are differences that were already visible from the other side, if you like. This looks like a formal exercise, but it turns out to be quite useful, not least because it turns out that m and m primed are identical if and only if they are equivalent according to both of these equivalence relationships. So that's quite interesting. It has the impact that now we can pick any old transversals for these pairs of equivalence relations, that is, any set of representatives for the equivalence classes, and then we can use them, if you like, as coordinates for the whole model set. So we can identify a model M by giving its tilde F equivalence class and its tilde B equivalence class, because this crucial fact tells us that there can't be two different models which share both a tilde F equivalence class and a tilde B equivalence class. And of course we can do exactly the same with n. Everything is symmetric. And then we can play some games with this. So suppose that we've picked our transversal m sub f, which gives exactly one representative of each tilde F equivalence class, and similarly for MB. We can represent our model sets conceptually on a grid, like this. And the crucial fact told us that no position could contain more than one element, because that would amount to having two models, m and m primed, which were different, but nevertheless were equivalent according to both of these equivalence relations, and that can't happen. What can happen is that positions can be empty. You could pick a tilde F equivalence class and a tilde B equivalence class such that there was no model that was in both of those equivalence classes. It turns out that consistency depends only on the F class of M and the B class of N. So once you've represented your models on grids, in order to know whether an arbitrary M and N are consistent, you only need to look at the column of M and the row of N. And maybe it's worth reifying that in our example case. What tends to happen is that the consistency relevant information is easier to identify than the rest. And so in our case, the tilde F equivalence class of the Java classes is given by the set of class names in it. That was the consistency relevant information there. And for the set of JUnit tests, the tilde B equivalence class was given by the names that appear in the tests of those particular forms. If we want to do forward consistency restoration, we don't need to know the tilde B equivalence class of the models we're restoring consistency on. We only need to know their tilde F classes. One thing that is important to note, though, is that although the result of R forward on M and N is the same as the result of R forward on MF and NF, that's what I just said, the actual result has coordinates that we might not in general know very much about. Okay, so we do know that by correctness, the row of the result, that's NB prime, must be some row which is consistent with the column that we had on the M side to start with, otherwise we wouldn't have successfully restored consistency, okay? There might actually be several rows which are consistent with a given column. That can happen. And in that case, the row we end up in is determined by decisions that were made by the programmer of the consistency restoration function we just applied. But there must be at least one. Also, the column of the element of the result, NF prime, might also have changed in the sense that it might not be the same as the column of the element of N that we started with, that's NF. Okay. That amounts to saying you might have changed the consistency irrelevant information in the process of restoring consistency. Okay, that can happen because of the way it's stuck to consistency relevant information. That's kind of where we came in. Yeah? Perhaps the old consistency irrelevant information just didn't fit together with the new version of the consistency relevant information. So the programmer of the restoration function was forced to change it. So an example is, if you have deleted a test class, then there is nowhere for you to put the body of the tests that used to be in the old test class. You've just deleted it, so that information has to go away, even though technically it's not relevant to consistency itself. So technically the way this can show up is that, having identified which row of the grid the consistency restored version of n is going to be in, you might find you have to move column, because when you look at the grid square that is in the intersection of the old column and the newly chosen row, that grid square is empty. There isn't a model there that you could pick to be the result. Okay, and exactly dually for r backwards. We've now introduced, at least obliquely, 3 different ways in which we might be in a particularly nice situation with the transformation, and beautifully it turns out they're all equivalent. So the first is to say that our bidirectional transformation might be strongly undoable, and the second is to say that the coordinate grids are full, or the model sets are full with respect to the bidirectional transformation. That means when we represent the model sets on the coordinate grids, every square in the grid contains exactly one model instance, as opposed to the potential situation in which some of those squares might be empty, as we were just saying. And the third one is, if you like, the consistency restoration process doesn't change anything that you might hope it might not have to change. In other words, r forward stabilizes the coordinate grid columns of n, and r backward stabilizes the coordinate grid rows of m. In other words, you don't get this apparently gratuitous change of column when you restore consistency, even though it was really the row that represented the consistency relevant information. So this is quite cute. And informally, these conditions amount to saying that the information relevant to consistency is independent of the rest of the information. And at this point, your satisfaction at that previous result should come crashing down, because you should realise at this point that although that's a lovely condition to have when you can get it, you can't very often get it. And so although it would be in some sense satisfying to say we will design a bidirectional transformation language which enforces that, which only allows us to write transformations which have those lovely properties, it would be too inexpressive. So that's a bit sad. We're starting to touch on notions of least change. So I talked about not wanting to change the column on the n side unless it was really necessary to do so because of an empty space or something. That's an example of the intuitively natural idea that we don't want consistency restoration to change more than it must change. There are 2 subtly different things. You might want to say that a small change on one side causes only a small change on the other. Or you might want to say that you can arbitrarily limit your exposure to change on one side by limiting the amount of change on the other side. So this amounts to saying, do you want some kind of notion of continuity or some kind of notion of openness, if you're interested in thinking about things from a metric or topological perspective? Unfortunately, discreteness messes everything up, and you can find convincing examples showing that pretty much every property of consistency restoration that you might think of enforcing is sometimes a property you will really want to violate. Again, it turns out to matter whether or not you're starting from a consistent point, so you get strong and weak versions of these properties. And I'm not going to say any more about that today, but there's a paper there that you can read more about it in if you're interested. So, problems we have. Each side has information that's not present on the other, and so lenses are not really enough pragmatically for our ideal situation. And in practice, information that's relevant to consistency is interdependent with all the rest of the information, so strong undoability is too strong a condition to expect to be able to insist on. You can start thinking about metrics for least change. You can say we would like to make the smallest change available, but what counts as a small change will depend strongly on your perspective, and actually you might not want least change with respect to it anyway. There's a lot more I could say here, but time forbids. And by the way, once you've specified a notion of metric least change, you can show that it's NP hard to do it anyway, so that's a bit sad, and that's all in the paper I referenced a moment ago. So in summary of part 2, it's fun to write down properties that you would like to have in your bidirectional transformation, but unfortunately you can't have them, or at least you can't have them all. different languages are good at different things, and therefore we really need them to be able to interoperate. We need to have a setting with lots of different models that may be related by bidirectional transformations in different languages, some of which may be specialist books languages and some of which may be general purpose languages. And in some cases the models may be related only by consistency checking, and we may also want different amounts of automatic consistency restoration in different cases. So we're really in a very highly heterogeneous situation. And that, I think, is really important. I've been talking throughout about the need, as I see it, to support a heterogeneous environment in which users may be able to incorporate bidirectional transformations which are written in a variety of general purpose or special purpose languages, and might expect to automate more or less of their consistency checking and restoration. I now want to go on for a few slides and talk explicitly about what happens when we go beyond just two models, and think about restoring consistency in collections of models when any of them changes. So here is a small but sufficiently large example megamodel. So a megamodel in this setting is any model whose elements are themselves models. So this is just a way of talking about the relationships between different data sources, where any pair or collection of them might itself have to be connected via a bidirectional transformation. So for the sake of argument, what we've got here is we've got a metamodel, MM, and we've got a design which conforms to the metamodel, and we have some Java code and a standard round-trip consistency relation has to hold between our design model and our Java code. And just to show that we can, we've got a ternary relationship between some Java code, some JUnit tests, and a safety model, where we might say perhaps that if the system is considered to be safety critical, then we need a more stringent relationship between the Java and the JUnit than we'd need if the system is not considered to be safety critical. And the notation here is just that the circles are representing sets of models where we expect to have at any one time a particular model instance in each circle representing the current state of that model. Models are shown in black if they are considered to be always authoritative. So if we're going to say the model is here because we need to talk about it in our consistency relations, but we're not entitled to change these models, then that's what the black means. So suppose, for example, the MM there might be the UML metamodel. It's not useful to fix an inconsistency between a model and its metamodel by changing the metamodel if the metamodel is a standard language that you're not allowed to change. In the case of the authoritative safety model, we have a slightly different situation where we might want to say the safety model must be entirely under the command of humans, and we don't want to allow our automated consistency restoration to decide that it would be awfully convenient if this system weren't to be considered safety critical, for example. Okay, so given that kind of setup, we can think about the consistency restoration problem, which is to say, supposing we're given some models, and some of them are authoritative, shown in black, and they're connected by some binary bidirectional transformations, or maybe more than binary. Going to talk about binary ones from now on. The problem is to find some sequence of applications of the consistency restoration functions that come along with the binary books that we've put together into this network, such that following that sequence of applications leaves you with an entirely consistent network. It restores all the consistency relations. Unfortunately, this is mostly impossible. You'd probably guess that. Several different things can go wrong. There might simply be no solution. So you might simply have constrained your setup too far in insisting that these black models have to be authoritative, and there might be no way of completing the configuration of network instances so as to be consistent with all of them. Or more interestingly, there may be a solution, but it may be one that you can't reach simply by applying the consistency restoration functions of the bidirectional transformations you're given, no matter how you do it. Or it may be that you can, but the order in which you do it matters, and you get different solutions depending on what you do. Now that might or might not be a problem, but under some circumstances it certainly will be. In some ways, the most interesting thing that may happen is that you may feel informally that the bidirectional transformations that you've been given, that you've put together into this network, that you've used as legacy transformations, are really able to do almost all the work, but just not quite. So you might want to say, suppose I could, I don't know, apply the round-trip conformance consistency restoration to modify the Java code to bring it into consistency with the design. Now, it's just that it's not quite now in the right state to have the consistency restoration function that connects it with the JUnit applied. But maybe if you could just do a small routine edit to the Java, then you could do the rest of the job by applying the other bidirectional transformation. So there's a certain notion of sort of fixing up that you might like to be able to do. And we'd really like to have a consistent way to talk about that that doesn't just enable us, doesn't force us to say, oh dear, you know, these bidirectional transformations we've been given just aren't good enough. So this is a job for David Wheeler's law. It says all problems in computer science can be solved by another level of indirection. So in this case we say, well, we understand about encapsulation and about agents, and so what we should do is we should say, given a model that isn't always authoritative, so a model that we would like sometimes to be able to modify automatically via a bidirectional transformation. So for each such model, we give it a builder, an agent, whose job is to be able to modify the model it's controlling in such a way as to bring it into consistency with perhaps all of its neighbours or a given collection of its neighbours. Okay? And it should be able to do it in some sensible way, which might involve invoking some bidirectional transformations that form edges of the network, choosing the right order in which to apply those bidirectional transformations, but also more intelligent things. Perhaps the builder might also be allowed to do these small edits in between applications of different bidirectional transformations that set things up to allow the bidirectional transformations to do the real work. Or indeed the builder might just do the work of restoring consistency itself. It could involve an arbitrary amount of computation. It might even interact with the user or apply some kind of search, some kind of machine learning, whatever else it might be. Okay? But provided that the builder of each model obeys its fundamental contract, which is to say, if you ask the builder to bring its model into consistency with a given set of its neighbours, in the end it either does that, it restores consistency according to the specified notions of consistency that are represented by the edges in that mega model, or else it fails, and we know that it's failed. Okay, so that was all about how we can talk about the process of bringing an individual model, an individual data source within our network into consistency with some or all of its neighbours, under the implicit assumption that its neighbours are themselves in a good state. That, of course, is only part of the problem we have to solve. We also want to be able to say, well, how do we do the overall process of consistency restoration in the network, bearing in mind that what we really wanted ultimately was to have all of those bidirectional transformations, consistency relations holding simultaneously in the model. And at the same time, we want some important properties. We want to know for sure that if the whole process completes without failure, then we really have restored consistency in the network, or in a certain subnetwork of it perhaps. And we also want to know that we haven't done unnecessary work, and we certainly don't want to end up going round in circles and never terminating, which is altogether too easy if you take a naive approach. Fortunately, it turns out that this is a very similar problem to that of building a software system from some sources, and that's an area where there have been some very interesting advances in recent years. And I chose to build on top of the Pluto build system from Sebastian Erdwerk and colleagues. I'm not going to say very much about it today. You can have a look at that paper at the bottom, and there's a separate talk which you can find on my YouTube if you're interested. The thing I want to draw attention to at the moment is the use of custom stamps to identify when rechecking is needed. So in a build system, you're familiar with the idea that timestamps are used in order to determine whether it's necessary to rerun a particular compilation step. If the sources have not changed since the last time the compilation step was run, then there's no need to rerun it. in our setting, it's very useful that Pluto allows us to have a more flexible version of that mechanism, which allows us to identify certain information which is relevant to whether it's necessary to redo a certain step, and more interestingly, when it's not. So we might want to say, okay, something about this model has changed, but actually we know that nothing which could possibly be relevant to this particular consistency relation has changed, and therefore we don't need to check consistency, let alone run a consistency restoration process, and that can save us quite a lot of work. And then there is, of course, some very interesting questions about, balancing the effort needed to compute the stamp against the amount of work saved. The process of using Pluto as a basis leads quite naturally to a couple of key decisions which are in themselves interesting, I think. One is that we have a build system-like approach, which is to say that we select a target, and then instead of rebuilding everything in the network, we only update those things which are transitive dependencies of the model that we're interested in working on. And this is in contrast to some of the earlier work on networks of models which had relied on spotting any change in the network and rippling those changes out through the network, which can be a lot of work and can also be quite disruptive and perhaps unnecessarily disruptive to people's work. So there are some interesting pragmatic questions about what the right answers are there, but I think that is interesting to think about. And the other is that we use an orientation model. So one of the key differences between the situation envisaged by Pluto and the situation that we have here is that we don't have unidirectional notions of what depends on what. We have bidirectional notions of what needs to be consistent with what. How are we actually going to handle that? Well, supposing that we have a bunch of different data sources or models, and we know that they have some kinds of notions of consistency between them, at some point we have to decide, if they're in conflict, which one is going to win. And we've talked about authoritative models in the past, so here the black models here are the ones which are always authoritative, which we're never going to want to change. What I've done here is to introduce a further notion of which models are authoritative right now. So on this particular consistency restoration process, this diagram indicates we don't want to change either the design or the JUnit models, but we're perfectly happy to change the Java model. Now it might in general be that you have multiple white models, multiple models that you're happy to change in your network, but as an assumption at the current state of affairs, all of the edges in the graph will have been assigned directions. So what you end up with is a directed acyclic graph superimposed on the mega model, and this tells us that we've already decided in which direction to resolve any of these bidirectional transformations where some kind of conflict resolution is needed. And that seems to work quite well at the moment, although I'll come back at the end to where we might perhaps want a bit more flexibility and might be prepared to pay the price of the extra complexity required there. So concretely, in order to use the mega model version of Pluto, which I should say is the merest proof of concept at the moment, it exists on GitHub, but it's in no way ready for prime time. The steps you have to take are you have to design your mega model, and in that way you create an orientation model like the one I showed you. Now the orientation model is just another model, and your users, most likely your project manager, might change it. It lives in your configuration management system, and so it might be that this week your project manager has decided that the design model is authoritative, perhaps because it's just been signed off by the customer and you really don't want it changed right now. But next week it might be the other way around. It might be that you say, well, okay, now we're confident in the correctness of the Java code and we don't want to change that, but we would be happy to update the design model in order to bring it into consistency with the Java model and what have you. And that's really a project management decision for software development. If we're in a setting where we have data sources which are related by consistency relations, then I think that's another question, and how often that would change I think is an interesting issue. Anyway, having done that, for each of the models that you might ever want to be able to build, so to modify in order to restore consistency, you have to write a builder in the way I described, and the framework provides a skeleton and some APIs for you to do that in an easy way, hopefully a very easy way if all your builder is going to be doing is applying a couple of bidirectional transformations. Of course, the more the builder wants to do that's not just that, the more work there will be there. But it's work which is controlled, and then the framework provides the algorithm for actually invoking the builders in the right order and under the right circumstances, and you as the user of this thing don't have to concern yourself with that at all. That's all done for you by the framework. Lots of future work needs to be done. There's some very mundane pragmatic work involving providing APIs for invoking particular model transformation engines, and there's some obvious things to be done about how do we generate these custom stamps that I've discussed, perhaps using slicing techniques or what have you. I'm interested in exploring the horizons, so trying to do a bit more sophisticated stuff, like saying, instead of deciding up front and recording in the orientation model which model should win in cases of conflict, so which direction a bidirectional transformation should be applied in, wouldn't it be interesting to take the idea that builders are agents even a bit more seriously and allow the agents to be autonomous or semi-autonomous in their negotiations with their neighbours, to use all relevant information to decide which of them should win in the case of conflict. So perhaps, for example, a builder might have access to knowledge of whether there is or is not anybody actively working on the model at the moment, and that might have an influence over how willing the builder is to have its model automatically changed right now. Any complex system like this is going to have to cope with failure and how to enable the humans who are ultimately in charge to cope with those failures, and that's a very challenging issue here, I think, but very important to get right. And that's only one aspect of trying to get this to the point where it can be used in practice to see how well it works. Along the way, I have a kind of niggling feeling, which is to say that I think we kind of lack a proper structure theory of models and relations. It would be really nice to have one, even better if it could be one that you didn't have to be a category theory expert to understand. We've talked about composition of models via bidirectional transformations, and we've seen a couple of different kinds of decomposition of models into parts. We've seen decomposition of a model into coordinates with respect to a given bidirectional transformation, and we've discussed the fact that those coordinates are not independent in general. I've just been talking about using stamps to say which parts of a model matter to consistency. I haven't talked about non-interference, although you might have inferred its existence. If you have two bidirectional transformations or more that impinge on the same model, we mentioned the fact that the order in which you invoke the transformations might matter. Sometimes it won't. Sometimes you'll know that they commute. That's called non-interference. A natural question is, well, what are sufficient conditions to ensure that two bidirectional transformations impinging on the same model are non-interfering? And in the paper accompanying this talk, I summarise some work that I've done on that recently, in which you can fairly straightforwardly identify some parts of the model that a given bidirectional transformation needs to inspect and those which it needs to modify, and some conditions under which you can say, well, if the parts that the two bidirectional transformations inspect and modify are non-overlapping in an appropriate sense, then we can guarantee that those things will not interfere. And that's another kind of decomposition. And all of these things are related, and it would be nice to have a proper structure theory, as I say. And I sort of have the feeling that maybe relations rather than functions between structures, between models, is what we really ought to mean in the long run by computational thinking. This feels to me more fundamental than the use of functions and sequential programming. But maybe that's a bit philosophical for right now. So to come back to Earth and back to the beginning of the talk, we talked at the very beginning about software engineering being too hard. And I talked about the problem that individual software developers are required to understand too much information, because although we separate concerns and we're able to give a particular developer one concern to worry about, in order to reintegrate those concerns, we often land the very same developers having to understand things about other people's concerns and things about the integration between the concerns, which make the task of software development very hard. And I hope I've convinced you that thinking about software development and perhaps federations of data more generally in terms of networks of chunks of data or chunks of information and bidirectional transformations between them can help us to manage those dependencies and to get closer to a world in which people can just work with their own concern and have the integration of those concerns largely automated. Now suppose we did that really well, to the point where the integration of concerns was as much integrated as it possibly could be. So we got rid of all the accidental complexity, and all that was left was actually genuinely important decisions. If we did that, then perhaps we could develop and maintain our software in a completely different way. We could envisage, instead of delivering software as a complete system intended to serve the needs of different groups of stakeholders whose requirements the software specialists have gathered. Suppose instead we delivered to those very groups of stakeholders each a domain-specific modelling language which recorded all and only the information that they need in order to specify their requirements with respect to their particular stake in the system. And then we were able to say, within this modelling language, you can change your decisions as your requirements change over time. And you can record your new decisions directly in your model. You don't have to come back to the software specialists and say, please update my software system and give me a new version. You can just do it yourself. And then we can use our clever consistency restoration technology to update other concerns as necessary, and ultimately to update the running software so that it's always up to date with respect to the latest requirements of all of our stakeholders. And most maintenance changes can be done actually by the end users without needing to come back to software specialists. Wouldn't that be great? Now, there's a lot to be done here, and obviously there are going to be times when people have to talk to one another. You can imagine things like, suppose our user interaction specialists at the top right, or maybe these are our people in the customer service department who know that customers are having a hard time entering data on some particular form. And they say, we would really like to remove this text field because customers find it irritating to have to enter this information. But then actually, when they try to update their model accordingly, it turns out they can't do that because the accountant says it's essential to have that information. I don't know, there's some regulatory purpose for it or something. Now, at that point, they really have to have a conversation. Okay, somebody has to decide whether you're going to collect that information or not. But perhaps it really could be at that level. Perhaps we could have sort of genuinely meaningful questions for stakeholders rather than having to have people do stuff that feels like programming. And that, I think, that's ultimately the prize. That's what would solve our software capacity crisis, because it would mean that the specialist expertise of our software developers could be dedicated to where it's needed, like writing the bidirectional transformations and the builders, and the decisions that are best taken by the people on the ground with the expertise in the particular domains could be taken by them instead of having to be filtered through software developers. And that, I think, would be really interesting. Anyway, in conclusion, using separate models, separated concerns, is vital, and it has underlain all of the advances that we've made in software engineering to date. Integrating them is hard, and that's not just because we haven't yet invented the one true formalism. I've argued that I think it's going to be essential to allow heterogeneity, so to allow relationships between data sources to be expressed in different ways, at different levels of detail, with different amounts of automated consistency checking and automated consistency restoration, and to allow gradual adoption and so on. So that heterogeneity is not an accidental temporary requirement. I think it's going to be something we have to deal with going forwards. I think there are important things to learn from how build systems work, and I think there are many interesting unsolved problems. Here are a few of them. Here are a few of the things that I could have talked about today, but mostly didn't. And before I ask for questions, I want to give a couple of plugs. So the first one is highly relevant. So this is the Model Driven Engineering Network. It's a UK-based network for improving model-driven engineering, making it more relevant to the needs of industry, and also to easing adoption by, for example, providing training materials and better communication between researchers and users of the technology. It's UK-based, but it's open to everybody. It's free to join. We have a whole bunch of interesting events like tool demonstrations and workshops and what have you. If you visit that URL, you can sign up for our community. Please do. Come and see if there are interesting things to you there. And the very shameless plug, because it's not really that relevant to what I've been talking about, this is my recently published book for students about how to write good programs. And I'm very grateful to Jeremy Gibbons, whom many of you know, for that lovely quotation about it. If you have students who would like help learning to write good programs, please point them at my book. Now, are there any questions?